Hi everyone. So I'm Zach. I'm the CEO of Aztec, and our mission is to provide practical programmable privacy on top of Ethereum and other permissionless blockchains. And yes, so I'm going to talk about Noir, which is our flagship privacy-preserving programming language, whose development is being spearheaded by Kev Wedderbaum. So I guess the first question is why a new language, given the proliferation of Snark languages so far? And it's because we have some very specific requirements. Noir is very much a privacy-first language for Snark, so it's not really focused much on scalability as much as ensuring that the user who is creating these proofs from circuits built by Noir can efficiently and effectively hide data. So we want to have privacy-preserving semantics built into the language, so the ability to create kind of private state variables inside a private smart contract type architecture. This will likely actually be a part of a framework that's kind of applied on top of the core language in the form of a library. And the focus is very much on efficiency and the performance of our proof algorithms. Doing a private transaction, you cannot delegate that proof construction to a third party efficiently without leaking secrets or information, which means that Noir proofs are typically going to be constructed on relatively wimpy hardware by users engaging in a privacy-preserving DApp, where they're likely going to be running this software in a web browser, so you're having to use WebAssembly to make the proof as well, which kind of even further limits performance. So efficiency is key, and that's why Noir plugs into our ultra-plonk cryptographic backend, where we have kind of hand-rolled sub-circuits for commonly used cryptographic algorithms, and allows us to do pretty efficient recursive proof compositions and other advanced cryptographic algorithms like SHA-256 and signature verifications. This is an open source project, and the goal is to support other cryptographic backends too, because Noir is deliberately architected to be proving system agnostic, which I can get to in a little bit. And the end game here is we want to use Noir to build privacy-preserving smart contracts that plug directly into a layer 2 architecture that we're building that's designed for that purpose. But more generally, we want Noir to be able to be used for a wide variety of cryptography projects that require strong privacy preserving guarantees. So a little bit about private smart contracts, because this is kind of more of a it's auxiliary to the actual language, but I think it's quite key because this is how we plan for the language to be used. Similar to how Solidity and isolation isn't particularly useful as a language, but because it is a programming language for smart contracts, that's where it has a large amount of utility. So if you think about typically if you want to do privacy preserving transactions, you need to do your database cannot be a traditional database like an Ethereum where you have accounts with balances that update, but instead you have need a more Bitcoin style type of UTXO situation where you kind of create and destroy these unspent transaction objects in the course of a transaction. But where a UTXO note in Bitcoin just represents some value in a more general system that's privacy preserving, these notes can be encrypted and they can represent as generic state variables. And the transaction rules around how you modify these notes can be modified by programmable Snark circuits. That's kind of the core of the high level of how state management would work. But if you want to build a privacy preserving layer 2 where you can where you can have user-defined smart contracts added into it, then you're effectively adding untrusted codec. The way that we're planning on permitting this is with a zkSessions style kernel Snark circuit. Well, influenced by zkSessions, where the idea is you have a Merkle tree of verification keys where each verification key maps to a private smart contract. And the kernel Snark circuit verifies the correctness of a single private transaction. So the kernel circuit will fish a verification key out of the Merkle tree. The user will provide a proof against that verification key that the kernel circuit will then verify, and also just ensure that the rules of their layer 2 are correctly followed, so that there are valid digital signatures from the transaction sender, that all of the semantics are correct. The proof of this kernel circuit can then be sent to a layer 2 aggregator, a roll-up proof constructor. And the entire process is privacy preserving because the kernel circuit is uniform, and any observer, third party, even the roll-up provider, has no understanding of the smart contract call within, or the identity of the users or senders or recipients, or knowledge of any of the state updates being performed, because they're all encrypted. So that's at a super high level, quickly, how one can do privacy preserving smart contracts. This is where Noir comes in. So the workflow for Noir is you take some front end, some use case that you want to write a circuit for. You write it in the Noir front end, and then that will get eventually spat out as both. You can then construct proofs over that program, and also will spit out a verifier smart contract that you can deploy to Ethereum to verify circuits. So this is eventually we will be verifying Noir circuits directly inside a layer 2, but for now in the alpha state, it just spits out a verifier smart contract you can deploy yourself to mainnet, and we will be maintaining this feature as time goes on as well. But the way that it translates a program into constraints is through an intermediate representation that's called SAS, so abstract circuit intermediate representation. It's a bit like an LLVM, but for snarks. And this is what makes Noir proving system agnostic. So right now we convert ASIA code into Plonk constraints through our Plonk cryptographic backend, but there's no reason why it can't be converted to RMCS constraints, or that can then be fed into Groth16 or Marlin. So we're hoping to add those in time, as well as the relevant verifier smart contracts for those different proving systems. So just to give an example of how ASIA works, the idea is that for commonly used algorithms, ASIA treats those as a black box, and it delegates the implementation of those to a cryptographic backend. So if you in your program want to do SHA-256, or you want to do range proofs, then it's up to the backend to convert those into constraints. And so, for example, with Aztec UltraPlonk backend, we have very efficient implementations of SHA-256 and range proofs and things like that. And it will be up to another backend, like if one wants to build an RMCS backend, it will be up to that backend to implement these black box functions in as efficient way as they can. And so the idea is basically, for most programs, what will happen will be the majority of the program code will basically just be calls to various black box functions with glue logic in between, and that glue logic will be converted into linear combinations that can then be very efficiently transposed into either Plonk constraints or RMCS constraints. So the high-level features that we want from Noir is, first of all, programs are directly compiled into circuits. We don't implement this through a virtual machine abstraction, although we would very much like to. The priority is proof efficiency. We just can't tolerate that when you're constructing proofs on an iPhone or a mid-grade consumer laptop. The proving systems that right now are orders of magnitude too slow to support that. That means that branching paths and non-constant loops are expensive. We want to eventually support them, but in a very limited capacity, so that we don't guide developers down a path where they're accidentally creating extremely expensive circuits. But we will be supporting eventually dynamic memory allocations, so vectors, dynamic arrays, those kinds of things, where you can access arrays at unknown, like prover-defined locations. We can do this because of we've integrated our ClickUp research into our UltraPlonk backend, which makes these kinds of constructions very efficient to compute, because effectively the typical way you would do as Alex said at the start, you would do memory access is through permutation networks, but because Plonk you can directly commit to permutations inside Plonk and prove their correctness, you can actually implement that kind of directly via the form of commitments, instead of having to validate the permutation inside your circuit, if that makes sense. I can go into that later if that's useful. So the performance targets for Noir are, so this is all using WASM, because that's kind of how we imagine most of these proofs are going to be made. Our cryptographic backend can already make basic proofs in less than 10 seconds on relatively average hardware like an iPhone 8 for circuits that have about 65,000 constraints, which is enough to do private tokens, value transfers, things like multi-sig wallets. But the target for the next 12 months is to be able to create these kind of advanced multi-recursive private smart contract proofs, where you have these inner proofs and kernel proofs, and to do that all in less than 60 seconds on average hardware. And the verify smart contract costs, I believe, about 400,000 gas right now to verify. We can probably optimize it down a little bit, but that's roughly, I think, where it's going to stay. Our development roadmap, currently the alpha that Kev's built is it's got an integration into our TurboPlonk backend, which is the variant of Plonk that we've deployed with we currently deployed to mainnet. And we have the basic pilot systems working, the Noir front end that can pass to Assay that then creates a prover verifier and the whole workflow. That's all being built out, as well as we support modules and standard library, which has these more advanced cryptographic functions like SHA and Pedersen and things like that. Target features for next year are more advanced. So we want to be able to, we will be supporting private state semantics and call semantics, so effectively a privacy preserving call stack. So this will be basic, very highly influenced by our private smart contract rollup architecture. And so these 2 points will likely be in like a framework that gets layered on top of Noir. We'll also be integrating into Ultradot backend. We'll be supporting more cryptography backends like for RMCS, for example, as well as a strong focus on developer tools, which are currently lacking because this is we're still in a quite early development phase. And then full integration with our private smart contract architecture. So if you want to get started, this is the link to our repo. I can post it in the chat afterwards, and I'll do documentation. If you are tinkering around with Noir, we would very much appreciate feedback, because we want as much information as we can get, so to further refine the language. And this is just a little code snippet for doing something, for doing like a tornado cache style deposit, where I can maybe I can leave this up if we have time for questions, but it's basically a simple membership check inside a Merkle tree to prove the existence of a variable in 3 lines of code. Right, so
cool.
That's everything.